Detuning harmonics by moving power capacitor banks lacks a direct formula. The process involves trial and error and requires a deep understanding of the power system and harmonic resonance. Here are some general guidelines. Firstly, move banks away from resonant frequencies. Identify the resonant frequencies where the harmonics are causing problems. Move the capacitor banks to a different location in this system where they will resonate less at the offending frequencies. Secondly, increase the distance between banks. Spreading out the capacitor banks can reduce the overall capacitance of the system, thereby changing the resonant frequency. Thirdly, install reactors. Adding reactors in series with capacitor banks can increase the total impedance of the system, which can shift the resonant frequencies away from the harmonic frequencies. Fourthly, change the capacitor bank size. Using smaller capacitor banks or dividing a large bank into smaller units can reduce the overall capacitance and alter the resonant frequencies. These are the steps to follow. 1. Measure the system harmonics. Use a vibration analyzer or other harmonic measurement device to determine the magnitude and frequency of the harmonics in the system. 2. Identify resonant frequencies. Plot the harmonic frequencies against their amplitudes. Look for peaks in the graph that indicate resonant frequencies. 3. Move the capacitor banks. Experiment by moving the capacitor banks to different locations in the system. Use the harmonic analyzer to monitor the changes in harmonic levels. 4. Fine-tune the location. Adjust the location of the capacitor banks gradually until you achieve the desired reduction in harmonic levels. 5. Verify the results. Once you have moved the banks, measure the harmonics again to confirm that the detuning has been successful. Detuning harmonics by moving capacitor banks is a complex process that may require multiple iterations. The optimal solution may vary depending on the specific system configuration and operating conditions. It is always recommended to consult with electrical engineers or harmonic specialists before making any changes to the power system. A deeper dive into each of these recommendations would involve a more granular look into the system. Measuring system harmonics accurately requires specialized equipment like a power quality analyzer. These devices capture voltage and current waveforms over time, which are then processed using Fourier transforms to decompose the signals into their constituent frequencies. The resulting harmonic spectrum shows the amplitude of each harmonic frequency present in the system, typically up to the 50th harmonic or higher. Analyzing this spectrum helps identify the dominant harmonic frequencies and their magnitudes. Identifying resonant frequencies is crucial because these frequencies amplify harmonic currents, leading to voltage distortion and potential equipment damage. Resonance occurs when the inductive reactance of the power system equals the capacitive reactance, creating a low impedance path for harmonic currents. This condition can be identified by observing peaks in the harmonic spectrum, where the amplitude of a particular harmonic frequency is significantly higher than the surrounding frequencies. Another method involves performing a frequency scan, where the impedance of the system is measured over a range of frequencies. A sharp dip in impedance indicates a resonant frequency. Moving capacitor banks to different locations involves strategic placement within the power system to minimize harmonic resonance. The goal is to shift the resonant frequencies away from the dominant harmonic frequencies. This can be achieved by considering the impedance characteristics of different locations in the system. For example, placing capacitor banks closer to the source of harmonic currents may reduce the overall harmonic distortion. However, it is essential to analyze the impact of capacitor bank placement on voltage stability and other power system parameters. Fine-tuning the location of capacitor banks requires iterative adjustments based on continuous monitoring of harmonic levels. After each adjustment, the harmonic spectrum should be re-evaluated to assess the effectiveness of the changes. This process may involve moving capacitor banks in small increments and observing the corresponding changes in harmonic amplitudes. The goal is to find the optimal configuration that minimizes harmonic distortion without compromising other power system performance metrics. Verifying the results of detuning involves comparing harmonic levels before and after the changes. This requires accurate and reliable measurement of harmonic distortion using power quality analyzers. The effectiveness of detuning can be quantified by calculating the total harmonic distortion, which represents the ratio of the root mean square value of the harmonic components to the root mean square value of the fundamental frequency component. A significant reduction in total harmonic distortion indicates successful detuning. The specific system configuration plays a crucial role in determining the effectiveness of detuning strategies. Factors such as the size and location of capacitor banks, the impedance of transmission lines and transformers, and the characteristics of connected loads can all influence harmonic resonance. Therefore, a thorough understanding of the system configuration is essential for designing and implementing effective detuning solutions. Operating conditions can also affect harmonic levels and resonance frequencies. Changes in load levels, switching of equipment, and variations in voltage and frequency can all alter the harmonic characteristics of the power system. Therefore, it is important to monitor harmonic levels under different operating conditions to ensure that detuning strategies remain effective. Consulting with electrical engineers or harmonic specialists is highly recommended due to the complexity of harmonic analysis and detuning. These experts have the knowledge and experience to accurately assess harmonic problems, design appropriate solutions, and implement them safely and effectively. They can also provide guidance on the selection and use of specialized equipment, such as power quality analyzers and harmonic filters. In addition to moving capacitor banks, other techniques can be used to mitigate harmonic problems. These include installing harmonic filters, which are designed to block specific harmonic frequencies, and using reactors to increase the impedance of the power system at harmonic frequencies. Active harmonic filters can also be used to inject compensating currents that cancel out harmonic currents. Selecting the appropriate harmonic mitigation technique depends on the specific characteristics of the harmonic problem and the requirements of the power system. It's also important to note that the interaction of multiple capacitor banks can create complex resonance patterns. When multiple capacitor banks are connected to the same power system, they can interact with each other to create multiple resonant frequencies. These resonant frequencies may be higher or lower than the resonant frequencies of individual capacitor banks. Therefore, it is important to analyze the interaction of multiple capacitor banks when designing detuning strategies. This can be done using computer simulation tools that model the power system and its components. These tools can predict the resonant frequencies and harmonic levels for different configurations of capacitor banks. The use of smaller capacitor banks or dividing a large bank into smaller units, as mentioned earlier, can help to reduce the overall capacitance and alter the resonant frequencies. This approach can be particularly effective in systems with multiple capacitor banks. By distributing the capacitance among multiple smaller units, the interaction between the banks can be minimized, and the resonant frequencies can be more easily controlled. In some cases, it may be necessary to use a combination of different techniques to effectively mitigate harmonic problems. For example, moving capacitor banks may be combined with the installation of harmonic filters or reactors. The optimal solution will depend on the specific characteristics of the harmonic problem and the requirements of the power system. Power quality analyzers should be capable of measuring a wide range of power system parameters, including voltage, current, frequency, harmonic distortion, power factor, and energy consumption. They should also be able to capture transient events, such as voltage sags, swells, and interruptions. This information can be used to diagnose power quality problems and to assess the effectiveness of mitigation strategies. It is important to calibrate power quality analyzers regularly to ensure their accuracy. Calibration should be performed by a qualified technician using certified reference standards. The calibration process should verify that the analyzer meets its specified accuracy for all relevant power system parameters. The data collected by power quality analyzers should be analyzed using appropriate software tools. These tools can be used to generate reports, graphs, and charts that summarize the power quality performance of the system. They can also be used to identify trends and patterns that may indicate potential problems. The software tools should be able to automatically detect and classify power quality events such as voltage sags, swells, and interruptions. This can help to quickly identify and respond to power quality problems. When selecting a power quality analyzer, it is important to consider the following factors: the accuracy of the measurements, the range of parameters that can be measured, the ability to capture transient events, the ease of use, and the availability of software tools for data analysis. It is also important to consider the cost of the analyzer and the cost of ongoing maintenance and calibration. In addition to power quality analyzers, there are other types of harmonic measurement devices that can be used to assess harmonic levels in power systems. These include spectrum analyzers, which display the amplitude of each harmonic frequency, and harmonic filters, which block specific harmonic frequencies. Spectrum analyzers are useful for identifying the dominant harmonic frequencies in a system. They can also be used to track changes in harmonic levels over time. Harmonic filters are used to reduce harmonic distortion by blocking specific harmonic frequencies. They are typically installed in series with capacitor banks or other reactive components. The effectiveness of harmonic filters depends on their design and the characteristics of the power system. In some cases, it may be necessary to tune the filter to the specific harmonic frequencies that need to be blocked. Tuning a harmonic filter involves adjusting its inductance and capacitance to achieve the desired performance. This can be done using specialized equipment and techniques. Harmonic filters can be either passive or active. Passive harmonic filters consist of inductors, capacitors, and resistors. Active harmonic filters use electronic components to inject compensating currents that cancel out harmonic current. Active harmonic filters are more expensive than passive harmonic filters, but they can provide better performance in some applications. The decision to use a passive or active harmonic filter depends on the specific characteristics of the harmonic problem and the requirements of the power system. When installing harmonic filters, it is important to consider the potential impact on other power system parameters. Harmonic filters can affect voltage stability, power factor, and other performance metrics. Therefore, it is important to carefully analyze the system before installing harmonic filters. It is also important to protect harmonic filters from overloads and other abnormal conditions. Harmonic filters can be damaged by excessive currents or voltages. Therefore, they should be protected by fuses, circuit breakers, or other protective devices. The location of capacitor banks can also affect the stability of the power system. Capacitor banks can cause voltage instability if they are located too far from the load. Therefore, it is important to carefully consider the location of capacitor banks when designing a power system. Capacitor banks can also cause resonance problems if they are not properly sized and located. Resonance can amplify harmonic currents and voltages, which can damage equipment. Therefore, it is important to carefully analyze the system for resonance problems before installing capacitor banks. In addition to moving capacitor banks, there are other techniques that can be used to mitigate resonance problems. These include adding damping resistors to the system, using tuned filters, and using active filters. Damping resistors can be used to reduce the amplitude of resonant currents and voltages. Tuned filters can be used to block specific harmonic frequencies that are causing resonance problems. Active filters can be used to inject compensating currents that cancel out harmonic currents. The choice of which technique to use depends on the specific characteristics of the resonance problem and the requirements of the power system. Harmonic resonance can also be affected by the grounding system. A poorly designed grounding system can amplify harmonic currents and voltages. Therefore, it is important to carefully design the grounding system to minimize harmonic resonance. The grounding system should be designed to provide a low impedance path for harmonic currents to flow back to the source. This can be achieved by using a solid grounding system or by using a grounding transformer. A solid grounding system is one in which the neutral conductor is directly connected to ground. A grounding transformer is a transformer that is used to create a neutral point for grounding purposes. The grounding transformer should be sized to carry the maximum harmonic current that is expected to flow in the system. The grounding conductor should be sized to carry the maximum fault current that is expected to flow in the system. The grounding conductor should be installed in accordance with the National Electrical Code, or NEC. The NEC provides guidelines for the sizing and installation of grounding conductors. The NEC also provides guidelines for the installation of surge protective devices, or SPDs. SPD are used to protect equipment from voltage surges caused by lightning or switching operations. SPD should be installed on all electrical equipment that is sensitive to voltage surges. SPD should be installed in accordance with the NEC. The NEC provides guidelines for the installation of SPD. The NEC also provides guidelines for the installation of arc fault circuit interrupters, or AFSIs. AFSIs are used to protect against fires caused by arcing faults. AFSI should be installed on all branch circuits that serve bedrooms. AFSI should be installed in accordance with the NEC. The NEC provides guidelines for the installation of AFSIs. The NEC also provides guidelines for the installation of ground fault circuit interrupters, or GFCIs. GFCIs are used to protect against electric shock. GFCIs should be installed in all wet locations such as bathrooms, kitchens, and outdoor areas. GFCIs should be installed in accordance with the NEC. The NEC provides guidelines for the installation of GFCIs. The NEC is a comprehensive set of standards for the safe installation of electrical equipment. The NEC is updated every 3 years. It is important to stay up to date on the latest version of the NEC to ensure that electrical installations are safe and compliant.